Hello again. So we have reached exercise on the graph edge property. So we need to classify the edges in the graph. We know that we can have three edges, back edges, or forward and cross edges. So in order to solve that, we will use DFS, and we will not just the visited array. So the visited will be have three properties. So it's either visited, unvisited, or explored. And we will say that if we move from an explored vertex to an unvisited vertex, it will be a tree edge. If we move from explored to visited, it will be a forward cross edge. However, if you move from explored to explored, so we have here two cases. So it's either it's just a bidirectional edge, for example, from 1 to 2 and 2 to 1, so there is no cycle here. However, if we move from 1 to 3 and then back to 1, here there's a cycle, because the parents, when I'm moving, I can move from 3 to 1 and then 1 to 3. So 1 to 3 is a forward edge, however 3 to 1 is a back edge. So we need to keep the parent of each vertex, and so this is it. So we'll do the animation of this graph. So here we have three connected components because the graph is disconnected, and we'll try to classify these edges. So in order to do that, so we will have three states for each vertex, so either explored, unvisited, or visited, and we'll classify the edges as three back or forward and cross edges. However, you may pay attention to the back edges, because if we move from explored to explored, it doesn't mean that we have a back edge or a cycle. So it may be just a bidirectional edge. So we'll start from DFS, so we'll pick 0. So in 0, it will be unvisited for now. All the vertices are unvisited. So, and when we start from 0, it will be explored. Then I will move to its adjacent vertices. So we have just one. So in one, first it's because it's unvisited, it will be explored. So in explored 1, so there's an edge to each adjacent matrix which is equal to 0. So here we move from explored to explored. However, here I should pay attention that it is not, there's no cycle here, it's just classified as a bidirectional edge because the parent of 1 is equal to 0, so I need to keep the parent. And then from 1 I will move to 2. So 2 it was unvisited, it will be explored, and from 2 again I can go back to 1. So 1, it's a normal back edge, there's no cycle, and from 2 again I can go from for 3. So 3 is unvisited, it will became explored. So here 3, I can move to 1. So when move to 1, it's from explored to explored. However, the parent of 3 is 2 and not 1, so it's classified as a back edge, and there's a cycle. From 3 I can move to 2, so it's a normal back edge, and from 3 I can move to 4. It's a forward edge, it's a 3 edge because it's from explored to unvisited, it will become explored. 4, it has just one adjacent vertex which is 3, so it's a normal back edge, and 4 finishes, so it's now completely visited, so it's now in black. I will go up to 3, so in 3 I have moved so I have finished all the adjacent vertices. Then I move to 2, and we have reached 1. So from 1 we have go from 2. Now we will go from 3. We'll go to 3. So from explored in gray to visited, it's a forward or cross edge. So this is classified as a forward edge, and then 1 finishes and 0 finishes. So for the first connected components, we have these types of edges. Then we'll move to 5. So 5 is unvisited. Since I will relaunch the FS from 5, it will become explored and then visited since there's no edges here. For 6, so we'll start the DFS from 6. So 6 is unvisited. It will be explored. So we'll move to its adjacent vertices. So first 7. 7 will be explored, and then we start from 7. So we have a back edge, normal back edge, bidirectional back edge. 7 finishes. Then from 6 to 8, to gray, to black, and then 6 is black. So those are the edges in this graph. So we need to implement this. So in order to implement this, we'll be using the same implementation of a graph, and I'll be using an enumeration here. So enumeration is just constants to not just say 0 or 1 in visited, it will be either explored, unvisited, and unvisited. So in the DFS, I'll be using the same implementation of DFS, just I will supplement it with an array called parent for the back edges in order to not classify it as a cycle. So it's just a two-directional edge. So we need I for loops, number of connected components, because we need to print the number of connected components just for printing. We need two arrays, visited and a parent, and let's initialize this too. So visited, let's just create it. So it's an int star. So I should have kept the implementation of all the DFS multiple malloc int. So the same for parent, and we need to initialize visited and parent. So at the first visited, all the vertex are unvisited, and we will implement, we will say that all the parents are equal to 0. So, and we will work on that. So we have for I equals 0, I less than the number of vertex, and I plus plus. I will place in visited of I unvisited, and in parent 0. You can place -1 if you want, depends on the on your code. So, and then we need to look over the connected components. So for I equal to 0, so I will launch. So if the vertex is not visited, so if visited of I equal to unvisited, it means I couldn't visit it, so there's multiple connected components. I will print the number of connected components. So from here I will initialize the number of connected components equal to 0. I will print the number of connected component %d, and I will increment it directly, and I will launch the DFS helper. I've called it here graph check. So it takes the graph, and the vertex that we are starting from is I, and visited and parents. So both arrays visited and parent. So this is for the DFS. So we go to the graph check. So in the graph check, we need, so as the DFS helper, we need to run over each the adjacent vertices as we have seen in the animation, and check the types of the vertex. So first, so I keep here some space for the declarations. So we just need an integer j for the loop. So first, as we have seen, visited of u would be equal to explore. So now we are exploring. So I will keep this here. It's more easier for me to copy paste the constant. So it's equal to explore, and then, okay, this is weird. It's to explore, and then we will move into the adjacent vertices of each element and check the adjacent, if it's adjacent, and do the calculations. So we are looping over the vertex, and if there's an edge from u to j, so if it's different than 0, let's write it equal to 1. So, and we will check the type of the vertex. So let's start. Let's start with the normal tree edge. So the one that we are moving here, it means the blue one. So the blue will not print it on the screen. So if visited of j is equal unvisited, it means we are still, it's unvisited, it's the first time. I will not print it on the screen. So I will not write tree edge unless you want to write it. So there will be a lot of output here. So I just save the parents of j, which will be equal to u. So we will keep that in order to check the cross edge. And I will relaunch the check on j, and we'll keep the same arrays. So this is for the normal tree edge. So I will not, if you want, you can print it here. Otherwise, let's check. So if the visit of j is equal to explored, so if I am from explored to explored, so I am from explored to explored. So here we need to check the parent, because I'm from explored to explored, from gray to gray. So we need to check the parents. If we have the same parents, it means just a two-way edge. So otherwise it would be a back edge. So we need here, so we cannot write this. So we need also to check. So if the parent. So we need to check the parents. If j equal parent of u, so it means that it's a two-way. So printf two ways, and we will print it like this. So from u to j, and from j to u. Otherwise, so if the parents of j different than parent from u, for example, like here, I'm going from 3 to 1, and the parent of 3 is 2, it's not 1, so it's a cycle, there's a back edge. So printf back edge, and the back edge, so there's %d, and we'll write cycle as in the output, and we have u and j. So this is for the back edge and the two ways. We still have the one that we are from the forward edge from explore to visited. So else, we have the else here. So if visited equal from visited to visited, so if I'm from u and I have moved from visited to visited, so it's a forward or cross edge. So we will print f forward cross edge, and we will print it %d. I will copy this. So however here there's no cycle. So, and at the end, after doing all the stuff, I need to say that the so after the for loop, that u is now visited. So we have finished. And this is it. So let's run this and see what we have. If we have some errors, so we have some errors. So let's see. There's a missing semicolon in the graph check. Let's run it again. Okay, what we have also, arrow v malloc. So we have int instead of void. So int star malloc size of grov malloc size of int. So maybe the error is before that. So expected, so it's 78. It's always the semicolon here. Let's run and execute. So we have an error in the multiplication. So int star, so visited and parents, they are both of type int star size of int. So maybe we have two size of int. Okay, so this is it. Look, so we have all the same output, so it's okay. And so this was for the exercise. Let me repeat. So we have just do the same DFS. However, the new here is that we have three states instead of just 0 and 1 visited or unvisited. And this is for the exercise. So it's a bit tough. And if you have any questions, don't hesitate to drop me a message, and I will answer you back. And again, thanks for watching.